Alright, hell yeah, I just got this new book, and we're going to do this problem. It's on geometry. It's the shortest walk of an ant along a cube. It's got to get from point A to point B. Now I just did a 2-hour video on this using a derivative, so I'm just going to go through and try to do it in the kind of the most concise way possible. So how I started tackling this problem is just, if something is if they're showing you something obvious, I'm going to go for that and analyze it. So if they're trying to get the shortest path from this ant from point A to point B, let's go along this line and then along B. And then for the problem, I said, hey, this cube has dimensions of 10, kind of all around. And so if we did this, we could figure out the length that the ant is going to travel, because we have to travel 10. And then we're going to use Pythagorean's theorem. So we're going to be along the hypotenuse, has sides of 10. So that's going to be the square root of 10 squared plus 10 squared. All right, booyah. And when we do that, we get 10 plus the square root of 10 squared plus 10 squared. And we get a length of 24.14. Now the easiest way to check to see if that is the shortest distance is just like, hey, just choose a different a different way. So I'm just going to come out here 1. That's kind of what I did in the video. And or let's do yeah, we're going to do that. So cool. So I came out a unit of 1, and now we're going to figure out what the hypotenuse of that triangle is. We have 1 and 10, and then the hypotenuse of this triangle, this isn't a 90-degree triangle, but this is. So I can know this distance, this hypotenuse, by saying this is 9 and this is 10. So that length is going to be the square root of 1 squared plus 10 squared. That's going to be this hypotenuse, plus the square root of 9 squared plus 10 squared. Okay, and let's just do that. So we got 1 squared plus 10 squared plus the square root of 9 squared plus 10 squared. And we get a smaller answer, so 23.5, so hell yeah. So that was pretty sweet. And we could do it one more time. Yeah, let's do it. Let's go at a distance of 2. So if we went at a distance of 2, our length is going to be the square root of 2 squared plus 10 squared plus the square root. So now this triangle changes. It has a length of 10, but since we came out 2, its length over here is only 8. So we have 8 squared plus 10 squared. All right, hell yeah. And so I'm just going to pull this up, and we have 8 right here, and then we have 2. So I just plugged it in my calculator. We get a length of 23.0. Okay, hell yeah. So it is a shorter distance. And then from this, I also realized visually that going from this point to this corner and then down was the same distance as going along this line and then at a 45-degree angle. So I noticed that those were the same paths, and the same process can be said if I come in 1 unit over here, then this hypotenuse is going to be my 9 by 10, and then this hypotenuse is going to be my 1 by 10. And so if I come in on either side, I'm going to get less and less. And just from that, then it could be, you could make the assumption that just even from there, that the shortest point is going to be in the middle. Okay, so hell yeah. So then what we're going to do is, do I have another sheet of paper? Hell yeah. Well, I can do it on this one, and I think it's good just to do it in one go so you can kind of see the difference. This value of 1, I'm just going to say is a variable x. And I can adjust that variable. I could say x is 1. That's what we just did. We said x is 2. And I could have said x is 3 and just kept going. And over here, instead of saying coming this direction, I could have said this is just x is equal to 9. So I could have said this is a value of 9. So then this hypotenuse is going to be 9 by 10. And that's how we got this value anyway, coming in by a distance of 1. So hell yeah, we would have had to use, and then same thing. All right, so we get that, and then so we want to vary this distance to figure out what's the shortest length to travel. So this is where we set up an equation where we say, hey, I'm not gonna just go straight to this point and then go at a 45. I'm gonna come down some distance, and this is what I'm gonna call x. So I'm gonna come down some distance x here and then go to b. But I realize from my equation, and let's just set up the equation first. So the length of this general equation, well, I know the first hypotenuse. That's going to be the square root of 10 squared plus x squared. Okay, but now what's this hypotenuse? Because this is not a 90-degree angle, but this is. So what I need to know this distance and then this distance. Well, I have one of them, but this is where I need to figure out what this is. And then so in the other video, I showed a good way to do this is like, well, I know this total distance is 10. You know what I mean? From there to there. And then I know one part of it is x. So now what is this? Well, you set up a little equation that says x plus something, that's going to be whatever this something is equal to 10. And then since this is an equation, you can solve for that something. So whatever this is going to be 10, bring the x to the other side, 10 minus x. So, or you can just, once you get the hang of this, because this comes up all the time in geometry, you know, just notice, you're just like, well, how do I get the other variables? You know, that's one way this one comes up a ton. So now I know that this equation, this hypotenuse, is going to be 10 squared plus this length is 10 minus x, so that squared. So we got 10 squared plus 10 minus x squared. All right, hell yeah. So now this is the equation for length, and I could just run it into my calculator. And so I could have 10 squared plus x squared plus the square root of 10 squared plus 10 minus x squared. Now this length is going to be about 25 high, and we're going to go from x is 0 to 10. So I'm going to do a little window. I'm going to go out to 10, maybe 11, and then I'm going to go up to 25. Okay, so hell yeah. So that's going to be the length at any value of x, and right in the middle is our lowest value of x. And so we can even, you know, kind of hone in onto this shape. So there you go. So our length has a minimum, but now we want to figure out, you know, if I didn't have a graphing calculator and I wanted to know what that minimum is, well, I know the slope of that line is 0 right there. So that's where we use this concept of derivative. So I'm going to say the derivative of this, in this equation, is length as a function of x. And for our problem, x can be between 0 and 10, so that's another aspect of an equation, you know what I mean? Just to like, hey, what are we honing in on, or where is the equation applicable? Okay, but now we're going to take the derivative of that, so the derivative of this length equation with respect to x. And what this says, I always do this. This is synonymous with change in length. So the change in this equation when we change x. So we're going to change x, and then we're going to see if we have a change in length. And so, and in the other video, I kind of went over that into more detail. But this video is going to be like, hey, let's say you just know this idea that if you have a derivative, it's going to give you the equation. All right, let's see if I can say this in words. So taking the derivative is going to give you kind of an equation of x, you know what I mean, this and that of x. And what that says is when you throw in that value of x, let's say of 0, it's going to tell you how much the length is going to change at that point. You know what I mean? So if you have 0, and it says basically if you went from 0 to 1, you know what I mean, as you start to go that direction, your length is going to... Oh, and that is fascinating because, like from this graph, our slope is negative right there. So that means if we're at 0, and we go in the positive direction too, from x is 0 to x is 1, our length is going to drop. You know what I mean? We're going to get more efficient in going from A to B. That length is going to reduce. Cool. And then so that also means the opposite though. If we get farther away, if we go x is equal to -1, you know what I mean? Let's say this cube extended this way, we would actually we would be, our length would increase. So that is fascinating. Okay, so that said, let's tackle this derivative. So we're going to have the derivative of, and I write in the whole equation, square root of 10 squared plus x squared plus the square root of 10 squared plus 10 minus x squared. And then put that in parentheses, and then dx. Okay, and now we're just going to use the properties that we know of how to solve a differential equation. We're going to use the power rule. This is, you just imagine this is to the 1/2. A square root is basically all this stuff inside to the 1/2. So we're going to bring down the power, so we're going to go 1/2, and then everything inside. And instead of doing the square root, because I don't know how it's going to change, I'm going to go just parentheses, 10 squared plus x squared, and then we're going to drop the power from 1/2 by a whole of 1, so it's going to be negative 1/2. Cool, and now we need to take the derivative of the inside. So do another parentheses, derivative of a constant is 0, derivative of 2x squared is just 2x. Okay, we're done. Go on to the next one. Same thing, we're going to bring down the power, so we have a 1/2. Take everything on the inside in parentheses. Okay, and then raise it to the power. The power drops from a 1/2 to negative 1/2. Cool, and then take the derivative of the inside. Now this, we kind of have to do, the same steps twice. Derivative of a constant is 0, but the derivative of this, if I just had this, I got to bring down the power, multiply by everything on the inside, power drops by 1, and then take the derivative of the inside. So we have to do, I'm kind of running out of room, so I'm just going to say, hey, let's do this. So we have bring down the power. So we're going to bring down that power of 2, everything on the inside, 10 minus x, and then the power drops by 1. And then we have to take the derivative of the inside. Derivative of 10 is 0, derivative of negative x is just negative 1. Okay, hell yeah. So now this is right there. So now we're done, and now we can, basically, well, I actually didn't solve this manually. That's for hella sure. I just plugged it in my calculator. So I'm just going to do, so we got 1, I guess I'll just write it like it is, 1/2, and then we got 10 squared plus x squared, and then we got 2 the negative 1/2, and then we have 2x, and then we got plus 1/2, and then we got 10 squared plus 10 minus x squared, all this to the negative 1/2. There's a lot of places to make errors in here, but we're doing pretty good. So we have 2, 10 minus x. We'll do the 1. You don't need to actually write that to the 1 power. And then, okay, hell yeah, let's see if we did this right. So, and I'm going to, and then, well, yeah, we're just going to do just a normal zoom on it. All right, hell yeah. So that's doing its line, and it crosses the it has a, so when we set this equation equal to 0, so this is the derivative of the length equation with respect to x. When the derivative is 0, when we find the point where we don't change, where the, back to that one graph where the slope is 0, that is going to be the location. That value of x is going to be the location where the length, in our case, is at a minimum. When you set the derivative equal to 0, you're either going to get a minimum or a maximum, and in this case, we get a minimum. And just with solver, we're going to find that value is going to be right in the middle at x equals 5. But I never even thought to actually try to solve this by hand. I think, I don't know if you could. That would be interesting. But hell yeah. So we get x equals 5. But yeah, it's kind of fascinating because, like, if I'm just using my calculator to solve for that anyway, why not just, we plugged in this equation and we saw that it had the lowest point. Why not also just use your calculator? You have a minimum and maximum on your calculator. So yeah, it's fascinating. But derivatives, I don't know, they just get hellacious where it's going to be hard to solve for that x as a simple equation. So then, it's good to have some sort of calculator to show that. But hell yeah. But just going through the process of what a derivative is important. Why when you set a derivative to 0, why that's going to be particularly important part, especially when setting up like optimizations. So this is that problem where you have optimization. Hey, you can take any route to B, but you want to take the most efficient route. Okay, hell yeah. And that's it. So we did it pretty good. Saved you 2 hours. And that's it. So guess what? That's a video. Alright, hell yeah. So this is the spider fly problem. We have a box, and now a spider is just 1 meter down on this box, and this fly is 1 meter up on that side. Now for this problem, the box has to be long, but it actually doesn't have to, I don't think it has to be that long actually. So that'll be for part 2, to be like, hey, does the box have to be a certain length? I think if the box is square, it works out, but I could be wrong there. But hell, this was such a cool problem because I did the problem of just a cube. This was, I have a book of kind of, it's kind of riddly problems, but we have, point A and B here, and I already did this video where you have an ant that has to get from A to B. And one aspect is you could just go like that. You know what I mean? So we can do the same thing with this problem. Be like, hey, I could just go this way, and then down, and then actually get a distance for that. So I'm going to have basically 10. I need to, like 1 here and 9 there, so that's 10, and then 100. So that's going to be a distance of 110. Then the question is, like, could I take a more efficient route? Could I go here? But yeah, and we'll explore that. Okay, and then so this box problem was pretty cool because I did the calculations that this was a longer route than just even coming 1 unit over and then doing that. And then so I was like, well, if that's the case, and then for this problem, I could see that if I went a 45 first and then down, that was the same as going here then here. So I said that I could come a 1 unit out that way, and that would be shorter. And then so somehow, somewhere in between these 2 points, I'm going to have the best result, and that's going to happen right in the middle. And this problem only had 2 sides. I had this there and this there. To actually put to values on it, I'm going to say we're coming down X, and this was going to be whatever this. I'll just say this was side A. And so this term right here is going to be A minus X. And then the length, and then so the length is just the hypotenuses. So this hypotenuse was going to be a squared plus x squared, a squared plus x squared. And then this hypotenuse, like where's my right triangle? Right triangle is down here. So this hypotenuse is going to be a minus x squared plus a squared. Alright, sorry, I'm beeping. Alright, and then from this simpler problem, this was an equation for length as a function of x. And we can optimize it. When x is 5, it's optimized. That's going to be the shortest distance. But then we can also take the derivative of this. So we can take the derivative of this equation with respect to x, and this gives us an equation of x. And then we would set this equal to 0. Because we know that, like, if we go along this route, hey, that wasn't very good. But if we go like 1 unit over, whoa, we get a drastic improvement. But then as we start approaching the right answer, we only get a slight improvement. So that improvement goes down. That's the definition of a derivative. And so when we get really close to the right answer, there hardly is any change. And so this value becomes 0. Like if we are just very, very close to, like if the right answer is 5 and we're at a distance of 4.99, we're not improving very much. If we go to x is 4.98, you know what I mean, or 4 or 5, we do improve. If we improve going this way, we have a lower length. Now this is kind of interesting because it's relative. Because also if I'm at x is equal to 0 right here, and all I go is to 0.01, like obviously my length doesn't reduce by that much. But now we need to figure out what, like, your proportion. So from x is equal to 0, taking this route, and then x is equal to 0.01, just a little bit, like, hey, my improvement is going to be better here than going from 4.9, getting really close to that optimal distance to 5. My improvement isn't that much. It's optimal right here, but I'm only improving just a little bit. So that's kind of the definition of derivatives. And so this basically, this little bit approaches 0. Like if I'm at 4.999 and I'm going to 5, I'm not going to get very much improvement at all. My improvement might be like 10 to the negative 6, 10 to the negative 8. It's approaching 0 the closer I get to there. Where on the other side of the spectrum, if I go 0 to 0.001, hey, I might have an actual tangible improvement. My improvement might be, even 0.01, percent of A. It might be 100%, so you get it. Big difference between this approaching 0 and this actually being some sort of value. Cool. So now what we're going to do is we're going to just try to set this up in kind of a technical way. And so I want to say, I kind of want to switch it. I should have switched the pictures. I'm sorry. If I print out more copies, I will. But what we want to do is, let's do this first, because we need to get an idea of what's going on with our problem. So 110, because maybe that is the best way to go. You know what I mean? So let's see if there was any better way, and what would be a better way. And I'm going to go this direction. I think visually I can see it a little bit better. So I'm going to try to, and this is the other aspect that I was pretty good at with these problems, coming from like a different perspective. If this is point A and this is point B, if you could go through this box, you would just travel this path. So I think we can all agree there. Now, I have this idea that if you get farther away from this line, like that's a bad thing. You know what I mean? If you stay the closest to this line you possibly could, that's a good thing. And this box is really visually tall compared to its width, but this part is square. That's kind of tripping me out. Okay, so with that said, like going up this way that's ridiculous, because you're getting really the hell far away from, like, you're not even, and then the other aspect is kind of like the dot product too, is like the dot product is like, hey, if I have a vector this way, like what's the dot product like along this path? Well, so then if this is the path I have to travel, what you kind of do is like you want perpendicular distance. So if I get up here, it's like, well, yeah, I did get, it doesn't look like I got any closer to B, but if I take this perpendicular distance, okay, hell yeah. So now I'm right here. So even though I had to travel 9 meters up, well, it looks like I gained a few meters. But now as I go this way, you know what I mean? Hell yeah. So now I only move a couple meters and I gain that. It looks like. So that's going to be an improvement. But this was kind of wasted. 9 meters up just to go a couple meters. And so the idea is if you can have a path that stays closest to this line, well then you're obviously going to be traveling down this line efficiently. And then for this problem, I did a solution where I saw some symmetry, because this is down at 1 meter from the base, and this is 1 meter from the base. So I said, I was just postulating, it's just like, well, whatever I'm going to do from this side to the midpoint, I am going to hit the midpoint at the same place on both sides. And we're probably going to have a straight line through here. And then this was cool, because if this is the midpoint of the box, and this line goes right through the center, so then when we have that, and this box has a dimension of 10, then I should have a length of 5 right here, a length of 5 right here, and then a length of 5, and then a length of 5. And then from from my idea that you want to be closest to this line AB as possible. If you're at the midpoint, you don't want to be down here because this is a diagonal distance. This would be an inefficient place to be. But if you were right here, that would be the most efficient place to be. And so I like that because that's where the solution takes us. Now I want to throw in like a side. If you want to try these problems for yourself, don't look. I mean, if you get the privilege, I got the privilege of seeing this problem, and then problems like these, it's like you really have to stay away from the solutions. If you want to do them with a fresh perspective and solve them yourself, you like even just glancing at a solution is like it spoils it. You know what I mean? And so, but yeah, I had the privilege of doing this problem and this problem. Well, I did this problem before, you know, happening to glance at the solution of how these are done. But I still am going at them from a different perspective. And this one is going to be using partial derivatives once we get there. Okay, hell yeah. So now I'm assuming that I want to go up the side of this box, and I don't want to. Like, so obvious, oh well, and then this said I got really far away. So obviously I just want to go straight down. So that's the first thing I did. It's like, hey, let's go straight down. And then, but I don't want to go straight over because I get into that same situation where I have to go up this side and I'm hella far away from my line. So then what I did is like, well, let's go, the first thing I did is like, hey, let's go to this midpoint. So I'm going to go to this midpoint. And then now where do I go? Well, I'm going to go straight up, I guess. You know, so that's what I did. I just went straight up to this corner. Like, honestly, in the intuitive process, I did this. But we're gonna sidestep that because I just said, like, hey, it's going to be symmetric. And going through this middle is going to be ideal. So then I just did this scenario where I was just like, well, let's divvy this up into quarters on both sides. You know, the box into quarters. And let's go straight down, come out a quarter. And then we're going to do the same thing. Straight up, come out a quarter. And then on this face, then we're going to go through the middle. And I thought that was pretty efficient. I was like, hey, it kind of follows the rules of what we're wanting to do. This distance is 100 all, so this distance is 25 to there. This distance is, so this triangle is 25. This triangle is 5. So we're going to go up 1. We have hypotenuse of a 525 triangle. Same thing here. This is down 1. This hypotenuse is a 525 triangle. And then we have 50 here. So this triangle, this hypotenuse, is part of a, well, let me get this right. Sorry, this is 50, but this height is 10. And sorry this box doesn't look square. I should go into Photoshop and chop it so it looks halfway square. I think I'm going to do that. If I get a new page, we'll do that. Okay, so we're getting kind of busy. But I think, let's grab a new page. So yeah, so we're going to say that I'm going to come straight up, straight down, divvy the box up into halves and then quarters. And then I'm going to come out to this point, go up to this point, come out there. So I think this hopefully is a pretty optimized line. So let's quickly run through the calculations. I have 1, I have 5, and 25 here. I have up 1. This triangle is a 5, 25 triangle. This triangle is a 50 triangle, and then up 10. Okay, so now the answer here, and I'm just going to do it in my calculator. So follow me. So we got 1 plus the square root of 5 squared plus 25. 25 squared. Plus the square root of 50 squared plus 10 squared. So we're just using Pythagorean's theorem. Plus the square root of 25 squared plus 5 squared. Oh, and then plus 1. Okay, hell yeah. So that distance right there is going to be 103.98. And that's better than just going straight up, straight over, straight down. That was going to be 110. So we do have an improvement. But then even from here, I was just like, well, maybe this isn't optimized. Because, damn it. And I already know the optimized answer. So this is really bumming me out. Because what I just chose right here is it's fascinating that this is This is, well, actually, let's change one. Oh, man. This is interesting. This is interesting because I actually did find out. See, this is, okay, if we're using derivatives, this is what you do. You know what I mean? So I'm going to say that this value of 20, so I'm going to bring up this equation again. Whoops. Oh, where the hell is it? Oh man, I think I lost it. All right, that's all right, because what we're going to do is we have a few things to vary. One thing is like, well, how about this 25? And since I kind of know the answer, I'm going to go in the wrong direction. I'm going to go, but what should I go? Should I go 26? You know what I mean? But maybe I'd miss the answer. Maybe the optimization is like 25.1. So if you're okay with analyzing small numbers and not making mistakes, what you would do is this. So we're gonna do the same equation since we have to rewrite it. We're gonna go down 1. Now this equation, I'm gonna say it's 25 point. We're just gonna do 25.1. You know what I mean? So there you go. Hopefully we're not going to miss an answer. If you thought you were going to miss an answer, then you would change this to 25.001. Do a thousandth increment. But anyway, so this triangle is now 25.1. This triangle is now 25.1. So if I'm going 25.1, how does this change? Well, now this is 49.8, and then nothing else changes. Okay, hell yeah. So now we're good to go. So let's do this. We got 1 plus the square root of 5 squared plus 25.1 squared. Cool. Now we're going to do this triangle. And we can see that we're just going to do 2 of those. So I'm just going to come over here, insert a 2. So we're just going to multiply by that 2. And since we're doing this 1 twice, I'm just going to do 2 there. And then we'll just have another square root, and it's going to be that one. So we got this square root of 49.8 squared plus 10 squared. Cool. And we're trying to improve. So let's see what we get. And we get 103.98. And I just lost that value. So I guess what we're going to have to do is I'm going to copy this and then change it back to 50.0 and then 25.0. And so this was our original 103.9803,903, and this new value, by changing it, is 103.9804. So this is worse. So making this 25.1 is worse. And so now let's go the other direction. Let's make it 24.9. And then this, so these are both 24.9. This becomes 50.2. Sweet. So I'm going to pull that equation up. We got 50.2, and then we're going to do 24.9. And this is exactly what a derivative would be. Hey, we're changing a value, and then we're seeing how that, like this is one part of an equation. Like the length of this is like adding this number to, doing the Pythagorean theorem on this number and that, and then adding 1 again. So by changing one parameter, we're getting this length is changing. So that's literally the definition of a derivative. Changing one aspect of a problem. How does that change like the equation that we're interested in, like the length? And so cool, we're doing it. So 24.9 and we did it. And so now we get 103.980 whoa. Yeah, my bad. I don't know. Well, no, this should have been an improvement. So let's see, where did we go wrong? I guess it doesn't have to be an improvement. Let's see. Oh yeah, I guess it doesn't have to be an improvement. You know what I mean? 24.9 squared. We got 2 of those, and then we're going to multiply by 50.2. That makes sense. If this is 24.9, this distance increases, and both of these are 24.9. Holy Toledo! So let's get it back to 50 just to compare, and 25.0. And so, oh man, yeah. So that's bumming me out because that was saying that 25 was optimized. And maybe I did the problem wrong, you know what I mean? So there you go. It looks like 25 could be optimized. I don't think so. But now we're gonna change one other aspect. And I think 25. That's the thing. Is like this is interesting. 25. I stumbled across an anomaly. It's not an anomaly, but 25 is optimized if we come straight down. If we don't come straight down, this number will change. So I guess from my analyzing of this problem, but that's sometimes you stumble right across the right answer, and then so this isn't the shortest distance, but if we go vertically straight up, then 25 is our answer. So that's what we just proved, and we just kind of stumbled across that. Okay, but now we know that, hey, I go straight down, but I'm heading over here. So maybe coming this way first is a better. And I could even go all the way to this corner and see if that's better. So now, I mean, we could do two separate problems here. We could say, but this is where you're, let's do two separate problems here because it shows you where you can, bite off more than you can chew. So if I go straight down and then over this hypotenuse 5 square root of 5, so let's write that. So we have 1 plus the square root of 5 squared plus 25 squared, and that's going to be the distance to get to here. It's 26.49. But let's say I go at an angle to this point and then just go over 25. Well, this hypotenuse is going to be the square root of 1 squared plus 5 squared plus 25, and that's going to be 30. Like, that distance is just obviously longer. So now, since we only moved this by a 0.1, we're going to do the same thing. So let's get another sheet of paper. So instead of coming straight down, this is half, quarter, and then the middle. So instead of coming straight down over to 25 and then up to the center and then just mirroring it, right? We're going to come down, and this distance is going to be 0.1. And then we're going to go over to 25, and we're going to see if that line is shorter. And this is pretty cool, which you can also do with paper. If you have a corner of a box, you can throw like if you have a card or something. I don't have any cards down here, but just a 90-degree angle into that box, and then and at an angle you're not going to get a 90. You know what I mean? Like, it might just be a little bit. Well, if you're if you're totally flat up against a corner, it will be 90. But if you that's if you just come in like straight vertical. But if you actually come in at an angle, then that angle gets more. And I definitely want to point that out because one of the things that I noticed with, and I'm going to do this box again because this was kind of a cool thing to visualize, is if this is point A and this is point B, and I come in to this corner and then down, there's an angle here. And so, and this angle is going to be, so if this is point A and this is point B, and this happens, where you have something like this angle is kind of sharp. Where if I come over to this halfway point, and let's just say it's not halfway this way, but when I come over here, the angle is less, and so what happens is, this angle is more. So this angle is more. This angle is more than that angle. So if I hit a path and then change. Like if this angle is more acute, and this angle is wide, I should just say wider because it's not an acute angle. But if this angle is wider, taking the more efficient path will have a wider angle. So right here, I can see that I chose this path straight down and over, and it has some sort of particular angle. Maybe it's 90. And then I can just see that if I do this, my angle widens. And so that's pretty cool, just slightly. But that also means that if I take this path, my angle must have sharpened. So that's kind of fascinating. Well, not necessarily. I don't think it had to sharpen there. Now I don't want to say wrong things, but yes, the angle for this new one should widen. So technically, I'm already kind of on point that if I go a distance of just 0.1 over at an angle down, and so again, if I do a blow up of that corner, I have something like this. This is 1 meter off. Instead of going straight down, I'm going to go 0.1 over. And then if this is my 25 out here, instead of going straight down into 25, I'm going to go 0.1 over and then to 25. And I'm going to find that this should be a shorter distance. So let's do it. So the hypotenuse of this one is going to be 0.1 squared plus this 1 squared. Cool. And now we're going to add it to, now we need to figure out what this distance. This distance is 25. This used to be 5 meters, but now it's 4.9. So now we have the square root of 4.9 squared plus 25 squared. All right, so hopefully this is an improvement. So now let's do just the straight down path, which would just be 1 plus the square root of 5 squared plus 25 squared. And yes, we can see that taking this slightly changed path is going to give us a better value, 26.48. So now we just know that we want to optimize that. So one way that we can do that is we can take a look at this corner. So we're going to draw that again. We're up 1. We know that we have to come down. We're going to make this x. So I'm going to come down x, and then I'm going to hit this 25. Okay, so now that I know... and we could do this in 2 different problems to show you that we need partial differential equations. I mean, because one aspect, yeah, this is fascinating because we've already shown that this distance of 25 is optimized when we come straight down. So now, I guess let's not, because let's just get straight to the differential equations. But since we found a more optimal path of just 0.1, now let's see if this 25 jives. So now our new distance to get to here, well, I guess the full setup is going to be, yeah, we got one more of them. Sweet. So instead of straight down, I'm going to come over 0.1. I'm exaggerating that. And then I'm going to come to a 25. Same thing here. Instead of going straight up, I'm going to go over 0.1. And then this is halfway quarter. And then I'm going to go at an angle to 25. So this is going to be 4.9. So we got 4.9, 25. This distance is going to be a triangle of 50 and 10. So now I can use, kind of Pythagorean's theorem to do this. I'm going to do the square root of 0.1 squared plus 4.9 squared. Hell yeah. So that's going to be that hypotenuse. And this needs to be 4.9. No, is that right? No. No, this first one is the sides of this hypotenuse has sides of 1 and 0.1. So we have 0.1 squared plus 1 squared. Okay, we're all cleaned up there. Okay, now we're going to, and we're going to have 2 of those. So we're just going to do this in one go. So we have 2 of because we're going to do the same thing. It's mirrored on both sides. Okay, now we're going to travel down this hypotenuse. It has a side of 4.9, so we can do 4.9 squared plus 25 squared. Cool. And we're going to have 2 of those too. Alright, so now, and then to finish it off, we just have this one hypotenuse. So we have, and it has sides of 50 squared plus 10 squared. Okay, hell yeah, and we get 103.9515. And that's better than 103.98. So technically, this is the best we've done so far. But this is now the goal, because this is going to be the moment where you're just like, oh, okay, now I kind of understand why we need like partial differential equations. Is because, is this optimized now? We thought 25 was right on, and now we're going to find that it's not. So I'm going to pull up this equation one more time, and we're going to go the other direction just to make sure. If we increase this to 25.1, this goes to 49.8. Oh, excuse me. So we have this triangle is going to be 25.1. We're going to have two of those. This triangle goes to 49.8. And hell yeah, so we're just good to go there. So now, is this better? This was 9515, and then this triangle is 9516. So no, making this, so we have a check that is not a more optimal route. But now let's go 24.9. This is the moment of truth, and as long as I didn't make an error, this will be more optimized. Just kind of the foreshadow. So if I go 24.9 here, this goes to 50.2. So I have 50.2 for this triangle. This triangle is going to be 24.9. And then hell yeah. And so let's compare these. This was 951519. This is 9513. So this is more optimized. You know what I mean? So let's keep going. You know what I mean? Let's go to, let's make this 50.4, and then this 24.8. You know what I mean? And hell yeah, that's now 95133 instead of 95139. You know what I mean? So hell yeah. So now 24.8 is more optimized. And I definitely recommend, if you're doing differential equations, do this process. You know, it's kind of like the mountain climber, the guess and check. And especially since you have a calculator, or hopefully you do, and then you can just re-up numbers, fairly fast. I could easily just change this to 24, and then I could, and then compare, and then go back and forth. And so I don't want to spoil the actual answer, because if we get it, we'll be excited that I didn't make any mistakes. Okay, so now what we're going to do, I guess I can point out that we said that this variable right here, we're going to say x, so x could be 0.1, you know what I mean? And that was just one place where that was better. We could do the same thing and change it to 0.2 to see if that's good, 0.3, hey, we're getting worse, come back to 0.2, come to 0.19, come to 0.18, 0.17, get worse, go back to 0.18, you know what I mean? And then just kind of do that process and then kind of hone in on an answer. So I definitely will kind of share, I guess, so this won't change much. I think it's about 0.2, 0.19, so that's what we get there. And then, and we could just do that. I mean, that's what I did to actually, I did that before being like, okay, now I'm satisfied that I have close enough answers, 24.8 and 0.2, let's say maybe those were close enough that I'm confident now that I could set up a system of equations and then have some sort of double check that I got the right answer. So for variables, so write down, well, yeah, hell yeah. So right here, I know that I can vary this distance. So I'm going to call this distance, do I have another sheet of paper? No. So we're going to print off some more. But we have this thing. We could go down 1, or we could go over this distance x. And then we have this kind of this quarter way, and then we meet at the halfway point. Now this could be y. And I was satisfied with calling these x and y. You can call them whatever you want. You know what I mean? But it made sense to me to call them x and y. And then we know that this halfway is 5. And then so if this is x, we say this is 5 minus x. And watch my video on the cube if you want to be like, yeah, that's complex to me. Just adding in these variables. So if this is y, then this hypotenuse, all the way up to the top of the box, so if I say this is y right here and this is y, and the whole box is 100, then this dimension right here is 100 minus 2y. Cool. It still stays 10. This is that 100 minus 2y. This is y. This is y. This is x. Because now let's just use this sheet of paper to figure out just a general equation for the length. So the length is going to be this hypotenuse, which is going to be 1 squared plus x squared. Cool. Heck yeah. and that's going to be that hypotenuse. Hey, we're mirroring it, so I'm just going to say that's 2. Okay, now let's go to this triangle. So this triangle, this is the 90-degree triangle. It has a side of 5 minus x and y. So we're going to have 5 minus x squared plus y squared. Okay, hell yeah. And we're going to have 2 of those because this is the same triangle. Okay, and now we have this triangle. It has a dimension of 10, so we do 10 squared plus, and then we have 100 minus 2y squared. But this is one of those, like if you've never done this before, and yet in college I would have never wanted to do anything like this. No one ever taught us stuff at this level, and I think it's just, it's like you don't trust that the math works. That's one thing, is just like, hey, you have this math, it's like, yeah, like the math doesn't lie. So that's one thing. You can make mistakes and then it's lying to you, but as long as you're setting up, especially geometry, it's like, hell yeah, all we're using is Pythagorean theorem to say, go into there, go into there, go into there. We do have variables. That's the only thing that's, kind of the trippy part. But we can say, hey, I can put in any value of x here, and I'm going to get those same values that I just threw, the same thing that I just did. I said x was 0.1, and that generated something. I said y was 25.1, then 24.9, 24.8. So this is the equation that I could start to optimize. And let's do this, because this is what I did. You might as well put it into your calculator. So we got 1 squared plus x squared, and then we got plus 2 square root 5 minus x. Even this is a good process just to see if you wrote it wrong. There's so many places to make errors, especially when things get busy. Whoa. All right, so now I'm 100 minus 2 alpha y squared. Okay, hell yeah. And then I got to throw in alpha. I got to throw in a value for y, so we're going to go 24.8. Stored as alpha y. That's what we're going to do there. And then this x, I don't know, we're going to do 0.1 stored as x. So now I'm going to bring up that equation, and we get 103.951. I'm going to change this x value to 0.2. Like, is that going to give me a better number? And it does. I'm 100. So now my best value is 103.94, changing that x to 0.2. I'm going to do 0.19 stored as x. And does that help my answer? I get 0.942. No, it doesn't. So 0.2 was better. Okay, but now let's change this x. So I'm going to do 0.19 stored as x. That was the best. Now I'm going to go and then just run the equation. Now I'm going to change this y value to 24.7. And do I get a better answer? Whoa, 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 whoa. So 0.2 stored as x. 24.7 stored as alpha y. Okay, so 0.942 is better than 0.94. We get 0.94256, 0.9424. Hell yeah, so that was better. So now we're going to do 24.6 stored as alpha y. This is now 24.6, and then my x was 0.2. So hell yeah. So these are the new values we're going to throw in. And do we get a shorter distance? Hell yeah. So now we're 0.9423. 0.9423 instead of 0.9424. So that was better. Let's go 24.5. Stored as alpha y. And we get 0.9423, but it's this was 3.4. Now we get 0.94230. Hell yeah. So at 24.5, that was optimized. Okay, now let's do 24.4 stored as x. And is that, whoa. 0.2 stored as x, 24.4 stored as alpha y. But I got to do 24.5 stored as alpha y. Bring it up again. All right, so we got that. So now I'm going to change y to 24.4. And then is this optimized? 103.94232. So no, this wasn't optimized. Okay, so 24.49, like, because 24.6 wasn't, 24.4 wasn't, but 24.5 was optimized. Okay, hell yeah. So that was optimized there, but now let's go back and change x. So so we have, so we're going to go to 24.5, stored as alpha y. This was optimized, but this is where our x is 0.2. So let's take our x to, x is, let's do 0.19 stored as x. And is this better? No, but maybe that's too much of a change. So let's go 0.199. So we're gonna bring up this value again, and then we're gonna go 0.19. Instead of 0.2, we're gonna go 0.198 stored as x. And is it up? Is it better? Hell yeah! Now we get 0.94229. So let's go 0.196 stored as alpha x. And we get 0.942291. Where this was 95, we get 91 now, 17. So I'm going to go 0.195 stored as alpha x. And now I go up to 8. Okay, so 0.196 was good. How about 1.197 stored as alpha x? And this doesn't take that long to actually chisel out an answer. And this was 0.925. So 25. So 0.9422917 was optimized. And so now that we know that this value is going to be 0.196, and we could still go back to the other way, but you kind of have to go this back and forth. Changing this value changes the optimal number for this, and finding the optimal number for this, the new optimal number, will change this value. So even if you do start to go back and forth, that is one of the parameters that you should play around with. Be like, well, I thought I found the optimal value was 25, but then we changed that parameter, and then this wasn't the optimal distance anymore. Okay, but we have something to shoot for. We have something to shoot for that this y is going to be 24.5, and this distance right there is going to be 0.196. And that's going to hopefully get us the lowest distance between these 2 points of 103. So far, I'll write this in, and then we'll start in with the partial differential equations. 22925. But, I mean, I don't know. Even if you already know how to do partial differential equations, I think this is still a good method, because it's like, if your life depends on it, that you get the right answer and not make any mistakes when you set up your differential equations. Why not do this? Because it helps you intuit kind of where those are. And then, yeah, it brings up those other topics like, yeah, this angle was sharper, this angle was wider, and hell yeah, that was the better way to get from those 2 points. All right, sweet. Okay, so now we are going to print off some more sheets, and we're going to do this partial differential equation. All right, hell yeah. So we're back, and we got this box looking, I don't know, just a little bit more to scale. Obviously 100, you're going to have to imagine that, but at least this looks square. And so, and this is definitely more than 1 meter high. And I'm just going to do a vertical line down and just show you that we're trying to optimize this. We're trying to have that a distance of x. This distance right here, since this is 10, halfway is going to be 5. If I'm saying this is x, then this is going to be 5 minus x. And I guess I can show you what I did in the other video, because this comes up a lot in geometry. Okay, I know this distance is 5, like this total distance, and then I know something about, in between. I know that this is going to be this variable x. So, and I can, and it's good just to, we said that x was going to be 0.1, and so, yeah, just to have that. If x is 0.1, well, what is this distance? Well, this is going to be 4.9. And then how do you write that as an equation? Sometimes it's hard because we have like a minus, but I know that this plus, I'm just going to do a question mark. Also, you can just do a box, like sometimes I like to do that. don't write a letter. I just say, hey, I don't know what that is. So then I can say x plus, something is equal to 5. So now I have an equation, and now I can solve for whatever that was. Just by taking x and then getting it over to this side by subtracting it. So we have that is going to be 5 minus x. Cool, and so that's what we have. 5 minus x is that dimension. We split this thing basically in half just because we have symmetry. That was the one thing that, hey, maybe that's a false statement, but I think we can go for it that we're going to have symmetry. We're going to do the same thing here, that we're going to do down here. And yeah, so we're at some point, somewhere around this quarter of the way mark, now this value is going to be y. Sorry I wrote all this, but and then so up here we're going to do the same thing. So this value is y. This would be vertical, so we're going to come here and then come over to y. So we have this distance is x. This is 1x. So we know this hypotenuse is going to be the square root of 1 squared plus x squared. The hypotenuse here, we need to know its length right here. That's y. And then right here, this is going to be 5 minus x. All right, so let's rewrite this equation for length, and then we're going to take the derivative of it. But we'll look that we have to take the partial derivatives of it. Okay, so to get from this to that. No, I didn't change the pictures, but obviously this spider is going to try to get after that fly. Alright, so this length is going to be the square root. The hypotenuse here is 1 squared plus x squared. Cool, and we're going to have 2 of those. And then this hypotenuse is going to be 5 minus x squared plus y squared. Cool, and we're going to have 2 of those. This hypotenuse, because we said that this is y and this whole thing is 100, kind of the same thing here. So now we have this distance of 100, we know that, and then we're going to come out y and then y. So we want to know kind of what this in-between is. So it's going to be this whole 100 minus y minus y. So it's 100 minus 2y. Alright, so and then the hypotenuse of this triangle is going to be, and we just have one of them, so we have 100 minus 2y squared, and this height is 10, plus 10 squared. Alright, and just double checking to see if we did this right. And this is cool because we need partial derivatives. Because if I just said, hey, what's the derivative of L with respect to x? You know what I mean? Well, and then that's just in general. If I'm taking the derivative with respect to x, and then I come across to y, it's like, what do I do? Well, we treat it as a partial derivative. And so we have this, funny little thing that says partial derivative of L. And then, I have to look this up. I mean, do I write partial derivative of x down there, or do I just say a partial derivative of the length? So I know the length's going to change when I change x. I have to figure out which one of these. How do you write a partial derivative? Because this was cool. This was the first problem that I've ever come across that I'm just like, oh, it's so obvious that x is changing and y is changing, and so I, you know what I mean? I can't just take the derivative of x, set that equal to 0, because, hey, this y value also has to change and optimize. Alright, hell yeah. I'm back, took a long break, so yeah, it is, you do it like this, it's partial. So it's partial derivative of your equation divided by a variable in your equation. And if anytime you see a partial derivative, it just means this equation has more than one variable that can be changed. So that's cool. And you know what I mean? If you go back and do basic problems, I don't know. You know what I mean? Typically, you're just going to change one variable, but it doesn't mean that simple problems can't have a bunch of different things that could change. And so that's fascinating that one problem of optimization that changes one thing. We'll see if you know what I mean, if you change another thing, if there's a point in there that you can also, you know, optimize. Some things are just like, you know what I mean, the smaller you make it, you know, it's going to be optimized where it just goes to 0, and the large, if you take that thing to infinity, it's going to be 0. But in this case, you know what I mean, we're kind of restricted. Y can only be, this distance can only be up to 50, and so if we went right to there, we'd have to go straight up. And so this is a perfect problem where y can be anywhere from 0 to 50, x can be anywhere from 0 to 5. And that's also good to have an idea of where, like, the parameters of your problem. Okay, hell yeah. So now we're just going to go for it, and and we'll talk our way through it, but just from the perspective of how you take a partial derivative. So we're going to be partial derivative of L, and we'll do x first. And right now we're just going to go through the actual process. So what you do is you just, if I'm taking the derivative with respect to x, I mean, just imagine this, you know what I mean? I have a constant, I have a square root, so let's just talk our way through it, you know what I mean? This is the same thing as this whole thing to the 1/2. A constant, if I'm taking the derivative, and then also taking the derivative of anything, if I take the derivative of 3 things that are added together, it's the same thing as taking the derivative of the first one plus the derivative of the second one plus the derivative of the third one. Also, if I have a constant out front, it's like, hey, I can just get that constant outside the derivative, and so now I'm just going to take the derivative of this. This is going to be everything in here to the 1/2 power. So I'm going to, the power rule says bring down that 1/2 power, still keep everything in here in parentheses, and then take that power, subtract 1. So this will be no longer 1/2, it'll be negative 1/2. Cool. And then you must take the derivative of everything inside. This is a constant, and this is going to be the derivative of 2, this is just going to be 2x. So we're done with that one. Now let's go over to this one and talk our way through it. 2 can be outside the derivative, and we're still taking derivatives with respect to x. So this is going to be bring down the 1/2, write everything inside here to the negative 1/2, and now we need to multiply it by the derivative of the inside. And we have 2 different terms. We have an addition, so it's the same thing. You know what I mean? We're going to take the derivative of the first one and then work on the second one. The derivative of this first one is going to be, and we see that it is a function of x, because if we get to this one, just to jump ahead, when we have to take the derivative of the inside, well, this isn't a function of x, so we have to treat this like a constant. You know what I mean? So it just becomes a total constant. And the funny thing is that you actually you wouldn't need, I want to walk my way through it where you don't have to treat this as a constant. And we'll do it for this one. So, okay, we're still taking derivative with respect to x. So we're going to bring down the power. So it's going to be 2. Write everything on the inside. Drop this power to 1. Cool. And then take the derivative of the inside. That's going to be, the derivative of negative x with respect to x is just negative 1. Cool, and so we're done with that one. But let's say instead of just treating this like a constant, which is also kind of just like a hand waving thing, we could just say, hey, let's do it. So we're going to treat it like it's a variable. So we're going to bring down the power. We're going to have 2y to the 1, and then we're going to take the derivative of the inside, which would be just, so it's fascinating how you can, I like to do this, especially when chain rule, it feels like only applies to, you know, things that have multiple things going on. But we can take the chain rule of y squared. So I'm just going to write this as y, just like that, squared. And then, heck yeah, I'm going to do it in the chain rule. Bring down the 2, bring the thing in the parentheses, and then drop the power. So bring down the power, write the thing in the parentheses, and then drop that power by 1. And then take the derivative of what's in the parentheses, but we're taking dy with respect to x. And then we can see that, oh, there is no x here. You know what I mean? There is, so this So then I guess, yeah, I'm still kind of new to this, but a little hand wavy, and we just got to treat this like a constant. But yeah, there is taking the derivative of y with respect to x. There is no x to take the derivative of, so this just this becomes 0. The derivative of a constant, the derivative of 3 with respect to x, same thing. It's like, hey, there is no x to take a derivative of, you know. Or if and another way to say it is if I have, well, I don't know. Visually, this one's, I haven't come up with any way to visually show this, but I mean, 3, the number 3 ain't changing, no matter if you change x, you know, something else. 3, that 3 ain't changing. So the and what is it? The derivative says if you change x, you know what I mean? So if I say x is 0, what is 3? So 3 is 3. So if this function is the function of 3 or whatever, cool. That stays the same. So this part still stays 3. Then I'm going to boost x to 1. And then what is this? Does this 3 change? No, this 3 doesn't change. And then, so let's write this out. So the derivative of 3 with respect to x, the derivative is very synonymous with the change in the number 3 with change in x. Cool. And then so the change in the number 3, well, it was 3 to begin with. It was 3 final. So you take final minus initial, and then divide it by the change in x. 1 minus 0. And then you get 0 divided by 1. And so you get 0. So that's, I don't know, like that's where I'm at in my understanding of the derivative of a constant, and is 0. But I swear derivatives are one of those things where it's like, I'm going to, the more that I learn about derivatives, I'm going to be constantly, you know, telling you, like stuff like that. Yeah, the derivative is basically, hey, we're changing this top thing. We want to know the change in length. So when we get an answer for this, it's going to say that's going to be the change in length when we change x by a certain amount. And because this is just a number, like when we do the derivative and then throw in a value for x, and in this case we'll have to throw in a value for y, we get a number, and in this case that's going to be the number. That's going to be, and it's going to be like maybe a negative change because we want to reduce our overall length, and so that's going to be at that value. Like let's say x is 0. That was the worst case when x was 0 and y was 25. That was kind of the longer way to go. So if we're there, that's saying, well, if I change x from 0 to 1. Then yeah, my overall length is going to decrease. That's what that number is. And this is also interesting. It's like when you get an acceleration term that says acceleration is negative 10, like gravity is negative 10 or negative 9.8. What is this term? And then the units on it are meters per second squared. I like to write it as negative 9.8 meters per second. Because then you can even take this number and then make it into a ratio. So I'm going to say negative 9.8 divided by 1 is meters per second. And then this is going to, it better spells it out. This is going to be a change in velocity of negative 9.1 meters per second for every 1 second. The same thing happens with derivatives. You know what I mean? You're finding the change in length given a change in x of 1 unit. You know what I mean? So then, and it's also good. All right, hell yeah, get a new battery in. And this is going to be cool because, you know, having gravity be like 10 or 9.8 or just a constant kind of messes with your ability to do derivatives. It's a great start because, you know, it's a constant. It doesn't change. And it's pretty cool. Let's say gravity is 10. That means if I jump off a cliff in 1 second, I'm going to have a speed. I'm going to go from a speed of 0 to 10 meters per second. And I'm going to have an average speed of 5 meters per second. So in a second, I'm going to go 5 meters. So it's really useful to kind of do that math. So let's say just for, like, what was our answers? You know what I mean? It's always good to have a general idea of the problem. Like the The scenario of just going straight across and straight up was 110. We were getting better to 103. So let's say this, yeah. So from here over, to just going straight down over to 25, let's say we get like 103.5. Now, we know that if x changes, because that's this whole derivative, that's the whole point. We know if x changes, and we start at x is 0 and we get 103.5, this derivative is going to tell us how much x is going to change when we change, or how much the overall length is going to change if we change x from 1 to, from this value from 0 to a unit of 1. So this whole distance is 5, and if we go from 0 to 1, it's going to tell us how x changes. And this is great to talk about, because let's say it says we're going to reduce, like what was our final answer? Our final answer was 103.94. So I have this kind of wrong. So let's say I was getting pretty close. I was getting a distance of 105 right here, and I could improve upon that. And so after taking this derivative, and when we do take the derivative, I'm going to get like something x. I'm going to put in x is equal to 0, and I want to know, and it's going to tell me how much my length is going to reduce if I change x. If I change x in the positive direction from 0 to the next unit, next to 0, like 0 to 1, is going to tell me how much that's going to change. And it's actually going to tell me the instantaneous change at that point, but just bear with me. Just pretend like it's going to tell me how much it's going to change from 0 to 1, because this is the number, and again, it's not a ratio, and so we can put 1 underneath it. That's going to be the change in length for a change in x of a unit of 1. And let's just say that this, I don't know what it's going to be, but let's say it's going to be negative, let's say it's going to be negative 2. Cool. So, all right, no, I got a legitimate one that we can put in, so sorry about this. So it should be the partial of L with respect to x. And so we're going to get an equation with respect to x. We're going to throw in x is equal to 0, and this number, let's say it just pops out negative 5. And so this would say that my overall length is going to be reduced by 5 meters if I change my x from 0 to 1. And that's not technically what it's actually saying, because this would be the instantaneous change, because then if I go over to x is equal to 1, it might give me, it might say that this is positive. It might say this is positive 4. You know what I mean? So then I totally overshoot it or something. You know what I mean? So this is only indicated at that instant. All right, hell yeah. But we know from kind of working through the numbers that this x is going to be like 0.2. Like that was optimized. So then let's go back to this value that we might expect. And we're going to say that, hey, we have a change in length of negative 5 per, per one change in x. And that, so this is kind of our, and we're going to say this is change in length. So we can use this as an equation. So now I have over here a change in length of 0.2. So now I like to use the idea that the units are the equation, especially to not like just, especially when things feel heady. So how can I want to know this change in length, but this is an equation of negative 5 change in length per 1 change in x. I'm only going to change in x by 0.2. So actually I just multiply these, the change in x's will cancel, and I'm going to see that 0.2 times 5, well 2 times 5 is 10, but 0.2 times 5 is 1. So I'm going to reduce my length by 1 meter. And so if I had this had this length of 105 just going straight down, using this partial derivative, it might say that I might get a number of 0.5, and I know optimized is going to be about 0.2, And so we're going to reduce our length from 105 to 104. And that kind of jives with the actual answer we're trying to find. But I was just trying to show you kind of just one way to use the numbers, or like when you do get the numbers, like what are they meaning? And so, and from that perspective, this is going to tell you, if I set x is equal to 0, how much my length is going to change. And so yeah, it'll be fascinating after we do this problem to go back and like throw that value in. And when we do take the partial derivative of this equation with respect to x, it's going to optimize x, but it's not going to care about y. You have to actually input a y. You could put you could input any number of y, and that equation is going to optimize x, because that's what we just did. We just went through and then took the derivative with respect to x. And that's the part where I struggle the most. Like, well, as like a, for myself, I want to know a geometric, relationship between, doing a power rule, especially on something complex, and the result it gives. So there is a little bit of a disconnect between there. But using those rules, we're still taking the derivative with respect to x. So that means that we're on our way to optimize x. Okay, so I'm going to rewrite this equation, and then we're actually going to, well, we're not too messy, but yeah, let's well, no, let's just go for it. So I am going to take the partial derivative of L with respect to x. So now we can just go do it. So we're gonna bring down the half. That's going to cancel with that too. We're just going to make life simple. I just put things in parentheses, so this is going to be 1 plus x squared. This is going to be to the negative 1/2. Now I'm going to take the derivative of the inside. That's going to be 2x. Alright, so now moving on to this one. Bring down the half. Cancels with that too. I put anything square root, just put it in the parentheses. Especially when you're doing derivatives, because you're going to reduce the power anyway. And you're going to have multiple things that are going to be to either positive 1/2 or negative 1/2, and it's kind of nice just to keep everything on the level. Alright, so we have 5 minus x squared plus y squared to the negative 1/2. The derivative of the inside is bringing down this, so we have 5 minus x to the 1 power times negative 1. Alright. So hell yeah. And this is all a product. Cool. And then to save space, I'm going to come right up here. And I'm going to take the derivative of this. So this, we do have a half. We have everything on the inside. 100 minus 2y squared plus 10 squared. And then to the negative 1/2. And then the derivative of the inside. Oh, and this is so cool. I didn't catch that. There is no value of x on the inside. So had I caught that just earlier, well, this is going to be the derivative of a constant. The derivative of that is a constant. And we could have done that whole process that we just did. I thought that was cool. Just treat it like there is a variable here. And then when you go to take the derivative of y with respect to x, oh, that changes everything to 0. And that's another thing to notice. Anytime you're taking the derivative, it is the derivative of like something, that is a product of a few things. You're always going to get a product, until you're done with that derivative. You're not going to get, I guess you could consider, I don't know. Anyway, I think that's a true statement. So yeah, hell yeah, the derivative of this is just 0. Because the derivative of the inside is a constant. And so that's where that becomes 0. So sweet, so we have that one. So now let's move on to the partial derivative of this length equation with respect to y. Cool, so now let's not make the same mistake twice. There is no y in here. So, and that's kind of cool doing this, because a lot of people teach like, hey, you have to treat this as a constant, but I just showed that you don't. You could just go through that whole process of the power rule, and then once you have to multiply by the derivative of the inside, this is a constant. We call that 0. but the derivative, and then we could even, and I love taking this where you have like x squared, and then let's do that. So we're taking the partial of x squared with respect to y. So partial of x squared with respect to y. And so treat this as a power rule. So we're going to bring down the 2, put the x in the parentheses, bring down the power to 1, and then take the derivative of the inside, but with respect to y. So again, there is no y here. So we have to treat that like a constant. So that's the point that you could treat it like a constant. And then so this value is going to be 0. So that makes this whole thing 0. And so, and then to take the derivative of this, bring down the power, take this to the negative 1/2, and then multiply by the derivative of the inside, which we just shown as 0. Or 2x to the 0. 2x times 0. So hell yeah, so there you go. So that's another way, instead of just kind of this hand-waving thing, that when you do partial derivatives, you just treat this like a constant. I think that's an okay, but I think that's, I don't know. Just any steps in the direction that kind of explain it geometrically or logically, or just a little bit extra explanation goes a long way. But then the thing that I catch myself with, I just find different ways to remember it. Even just this, there might be nothing extra special. I just went more steps to show that the partial derivative of x with respect to y is 0, and that's treating x as a constant. You know what I mean? But it was just fascinating that there technically there was no difference in just hand waving, saying, hey, if I'm taking the partial derivative of this with respect to y, I treat every other variable besides y as a constant. But yeah, so there was no difference in just saying that and going through the whole process. But it was just fascinating that you can still go through the whole process of thinking there's a variable inside, but then that variable is a constant. Cool. Okay, moving on. So we're going to do this. The half comes down, cancels that 2. We're going to have 5 minus x squared plus y squared to the negative 1/2, and then multiplied by the derivative of the inside. So with respect to y, this acts like a constant. So we're going to do that now. And then this is going to be 2y. Cool, done with that one. Let's go to this one. It has a y in it, so that's good. Bring down the power. We're going to have 1/2. Rewrite everything inside. Plus 10 squared, and then bring down, and then drop the power by 1. So this is going to be negative 1/2. Take the derivative of the inside. This is a constant, so that's going to be 0. We got to take the derivative of that. And use the power rule again. 2 comes down. Again, write everything on the inside, and then drop the power by 1. Alright, sweet. So, cool. And then take the derivative of the inside. So we can take the derivative of y. Negative 2 is just a constant, so let's do that. So we just have negative 2, and then isn't that fascinating? Even when you're taking the derivative, so if we have derivative of negative 2y with respect to y, you can just know that that's going to be negative 2. Or another way to do it is like, well, what do you, is it a scalar? I don't know if you call it a scalar, but just the constant outside, all constants can just come outside of the derivative. So this is the same thing as negative 2 derivative dy of y, and then hell yeah, then you just know the derivative of y with respect to y, and that one's cool because it's just dy, and it's even just visually 1. Anything, any number divided by itself is going to be 1. And so any equation, even if I had like x squared divided by x squared, we know that to be 1. There's a lot of things like that. Square root of 1 plus x divided by the square root of 1 plus x. You can get as complex as you want. Any function divided by itself is just 1. Cool. So we could just get that negative 2. Alright, hell yeah. So we did it. So we get these two equations. Now what? What do these two equations tell us? Well, And then what do we want to do with them? Well, we want to set them equal to 0. So we want to set both of these equations equal to 0. And because that's when they're going to be optimized. We said that if we throw in a value for x into this one, and just setting y to be 25, I really kind of want to do that. So yeah, let me type this into my calculator, and then we're going to double check that. But it's also good just to watch me type this in to see if I can do it fairly fast, fairly accurate. I just do negative 0.5 for this, and then 2x plus 5 minus x squared. Now any y term, I gotta change. Like my calculator doesn't do y. Y is an x. X is the variable. Y is the equation. So if I'm gonna say that this is a constant, I gotta make a new variable for it. So I'm gonna say plus alpha s squared. Cool. And then parentheses to the negative 0.5, 2, 5 minus x, negative 1. All right, hell yeah, so let's just double check. We got a negative 1, 5 minus x, we got a 2, we got a negative a half. We have this as s squared, and then we have 5 minus x squared. We have 2x, negative a half, 1 plus x squared. Cool, so now I'm going to I'm going to put 25 stored as alpha s, and now we can graph this. Now we know what length is it going to come out. The length is going to be 100. So anytime you're graphing something, for sure, just go right to the window, because that's a good indication you know what the graph is going to be of. We know we're going to get a length close to 110, and what's our input? Our input is x being like somewhere between 0 and 0.2. So actually we're going to do this. We're going to go x is negative 0.1 to positive 0.3. We're going to have we know we want a length of somewhere between 110 and 100. So my y, I'm going to be y max is 110, y min is 100. And that's just so cool that you can do that and then kind of get unless I just totally messed up the equation. Check it out. Yeah, it's not even in there. Oh, I'm so glad I did that, because that just shows, I just said, anytime that you write an equation, you should have a window trying to tell you what the hell you think it should be. And we just spent that whole time saying that we're going to get a differential equation, or a partial with respect to x, that's going to be this one, where when we throw in x is equal to 0, you know what I mean, that's going to be straight down. We're going to get a value of like 105. You know what I mean? And then it can be improved upon. There's going to be a point where x is, 0.2, and this equation is going to be 0. So now I know that my x is going to be anything between 0. So let's go back. X is going to be anything between 0 and 0.3. So we can do negative 0.1 to 0.3. And my y, the actual value, it might only be like 5. Let's say it's just, let's say it's 10. And then my minimum is going to be negative 1. So hell yeah. So now this will show us. And, oh, my bad. And, oh, that's so fast. This is going to be negative. So if I did it like I thought I was going to do it, I thought this was going to be, my max would be positive 1, my min would be negative 5, but I was still way off. When we throw in x is equal to 0, the change in length was hardly anything at all. So yeah, now I'm kind of fascinated. So we're going to throw in that value of 0. It gives us a negative 0.39. And now I want to go back and talk about this because this is so fascinating. So we're going to go back to our equations for just for this. Oh yeah, let's see. Yeah, I'll pull one up. Should be pretty simple. Okay, so here's one of the equations. We have the first. Whoops. Alright, so this first hypotenuse was going to be 1 and then x. So 1 squared plus x squared. The second one was going to be 5 minus x squared plus y squared. Cool. And then this last one was going to be 10 squared plus 102y. Cool. So I'm just going to throw that. And then my y, we were going to put 25 stored as y. My x is going to be, x was going to be 0. So 0 stored as x. And then this was going to be, so this gives us a value of 103.98. Oh, so here's where I was mistaken. I didn't know this value was 103.98, and then optimized was only 103.94. So we're only reducing, we're only improved by moving x. We only improve by 0.04. All right, hell yeah. And we improve our length, so our change in length can improve. It can reduce by 0.04 when we change x by 0.2. So let's do that. So 0.04 divided by 0.2. So then negative 0.2 would be the value that I would expect when I have this equation graphed and I throw in a value of 0. And I actually get negative 0.4. And now that makes perfect sense. And I'm going to talk about that. Because this is cool, because we can't change x by very much. So this equation can't be like wildly rapid where, you know, like this is my change in x of point, well, yeah, I was thinking my change in x was 0.2, but that would be an indication that it was like this the whole time. But we can't have that, because we know if it's like this the whole time, then there's going to be a place out here that's way more optimized. So we still know that this equation has to go through 0, and it ain't making a hard corner like that. So, and more realistically, it's going to take a line like this, so we're going to have, but the only way to still have that same change of 0.4 is to have an average of negative 0.2. So our change in length is negative 0.2 meters, that means that this value has to be negative 0.4 meters. So I think this stuff is really cool just because you're analyzing what the graphs could be, and this is going to be very helpful when, you know, little mistakes start to pop up. But this is, doing this stuff is one way that I can prevent making, just a lot of mistakes. And sometimes you'll make 3 mistakes at the same time, and they're very hard to fish out. Sometimes it's just one, and then you can kind of go back and find those. All right, hell yeah. So I think we thoroughly showed that this equation is right on. And this equation has a 0 value, so we can even find the 0. So we'll do a left bound. You'll have to bear with me. But yeah, this was the partial derivative with respect to x. And it says that at 0.192 is the optimal. But that we already inputted this y value, or in our case, alpha s. So into this equation, we said s was 0.25. You know what I mean? And so this just chiseled out a value of 0.923076923. I should just store this as alpha a. But now we're going to change s to 24.5, which we thought was optimized. And we're going to store that as alpha s. And then we're going to graph that. But let's get a little bit closer. So we're going to have negative 2. Cool. So now we're going to graph this. And we're going to get a different optimization because we changed our y value. So I'm going to go for a value of 0.2, get a 0, left bound, left bound, right bound. Alright, sweet. So this gives me optimized x is 0.1960784. So is this, well, it's different. You know what I mean? This is 192. This is 196. But we just know that this is going to be more optimized because we already kind of crunched the numbers before. So it just shows you that, yeah, this is going to optimize given whatever value of y you put in. So it's treating y as a constant, and that also explains why we took the partial derivative. When we took the derivative, we just ignored y or treated it like a constant. So then when we set this equal to 0, that's kind of optimization. That's where, this equation, and I really don't want to do it, but we could do the same thing to this equation. We could write this equation in and have y is just, 20. We could just change y. And I think we need to do that. So I'm going to erase this equation. We're going to type this one in. And it's just good skills to type these equations in. So we have, I'm already to there, plus square root 5 minus x squared plus, see here I'm just going to type in alpha s, because my calculator won't like y, plus the square root 100 minus 2 alpha s squared plus 10 squared. But yeah, just so many places for little errors. We'll see if we can find any. I don't think so. I think we're pretty good to go. Alright, sweet. So now we're going to graph this. Now this was what I was trying to do. So wait, alpha s, what do we have for that? So I'm going to put 25 stored as alpha s. And then, cool. And now we're going to graph this. And so this is going to say x is anything between 0 and 5. So we're going to go -1 to 6. And then this is going to chisel us out a length. And that length is going to be somewhere between 110 and 100. So we're going to go max of 110 and minimum 100. Alright, let's graph it. And hell yeah, we get a nice little, you can see that we get a low point. And that is probably more important to show you this graph than the other graph that went through the x. This graph went through the x-axis where x was optimized. This shows you the minimum length, actually visually. This is what we just did is type this equation in, and we just chose a value for y. Because that's what you're going to have to do. This equation has two values. Two variables, x and y. So I'm just going to say, hey, I'm just going to guess y. And so that's what we did. We threw in 25. And this equation shows you where x could be optimal. And it's right at that low point. And most all graphing calculators have this ability to find minimums. So I'm going to go to that value of 0.19 and then I'm going to find the minimum. So I'm going to go left bound of that minimum, right bound, and then right on that minimum. And so we get this value again that we already found. We already found from this equation. So we have a check on reality there. Now I'm going to say 24.5 stored as alpha s. Graph that. Whoa. 24 stored as alpha s. Okay, and now we're going to graph that. So we're going to get a new graph. We're going to find that minimum, and it's going to be that length. So the minimum is 3. Okay, hell yeah. And so that checks. We have a check on reality. Okay, booyah. So now we do the hard process of trying to find a solution. So what does a solution mean? Because then we could do the same thing to go to this graph. It says we have to choose a value of x. So let's just choose this one. Hey, that looked pretty darn good. And then we're going to optimize y. And, well, this is kind of cool because this shows you like an iterative process. Because then once I do that, I would optimize y, and then I'd go back and then throw that optimization into this equation. And I'm just fascinating if you did that, you always will approach a number. But you know what I mean? And don't be shy to do that. I'm not going to do that for this video, but maybe on my spare time, I'll do that. I'll just kind of choose random values. I'll start with x. I'll start with this y value of 25 like we did. You get this value for x. And then what I could do is take that value for x, throw it into this equation, which optimizes y. And so that's going to give me this new value for y. It might not be 25 no more. It's going to be like 21 let's say it's 24.6. So then it gets close to that 24.5, which is the actual answer. And then I'll throw it into this, and then I'll optimize for x. And then it's going to give me a little bit better answer than even this one. Well, no, this was the right answer. You know, so it's also good to have the right answer as well as doing a double check to see if you are converging. But I think that would converge. So I think that would be kind of a cool way to do it. So now we're at the process where we need to understand what these equations are. But I guess it's actually fairly simple. That was kind of the wild thing. It's like, even though you have a lot of complexness going on, you have two equations, two unknowns. And if you solve both of these equations, like a system of equation, there's equation 1, there's equation 2. The only variables are x and y, and they're in both of them. And so now, how do we solve systems of equations? And this is where solving differential equations, this is why you go to college for learning how to solve differential equations. But I would just rather do it from a numerical method. And I don't know. I feel like people think it's cheating, but no, it like opens up your world when you actually, kind of do this guess and check approach, because you really get hands-on on the graphs. And then you're not messing up, because they're like, even when I type this one in, I thought I was typing this one, so my window was just totally off. And you know what I mean? Those things are cool to have. Those like, oh yeah, aha moments of, yep, I'm not that great at visualizing a graph of a derivative. You know what I mean? Cool. I know that this is going to have slope. And we're going to have a negative slope right there, a slope of 0, and a positive slope. And it looks like this positive slope is going to be less changing than this positive. So even like right here, this might it's approaching a constant number. So then even from here, I know my answer is going to be a negative value. And I know this is going to be a fairly straight line. Anywhere around a 0, your line is going to be fairly... Is that true? Or is it going to be the most changing? Yeah, because the second derivative says that anywhere around a 0 point, you're going to have the highest change? You're going to have the lowest change in length, that's for sure. With changing x. That's the whole point of taking this derivative and setting it equal to 0. But then the question is the change in the change of x. You know what I mean? Because I see this just kind of getting steady. And this has so this derivative is going to be a pretty large positive number, or just a positive number in general. But the second derivative, the change in the change, is saying, hey, this is the slope here, but then right here, this is the slope. Where when you have a minimum, your slope is here, and then just a few seconds later, it's there. So this change is very substantial. So that's also kind of there's a lot of mind-melting things with derivatives, you know what I mean? And just kind of hash them all together is kind of interesting. Yeah, so the second derivative, when you have a minimum, that's going to be your largest change. Okay, sweet. So what I'm going to do is probably get a full sheet of paper without this box on it. I'm going to rewrite these partial derivative equations. I'll try to write this top one too. And then we're going to try to solve them. You know what I mean? We have to, and we could, I might, since this video is already hella long, we might solve it both ways and then just kind of double check our answer just to make sure. And then this is where some differential equations aren't very solvable. But this one is. I can actually, because look at this. We have x, y, 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 y. Sweet. I only have one value of x and a bunch of y's, so I can solve this equation for x. I mean, that perfectly says, I think that's probably also, if you're wondering if it's solvable, like fairly easily, Well, that's an indicator. If I only have one of these x's, well, I'm good to go. I can literally get everything to that side of the equation and just have x over here. And then I can take that madness and then throw it into every one of these x's. So, but I've already done this before, so it's good. So we can rapidly simplify, and then we'll get something like x is like, 5 minus y divided by y, something like that. I think that's kind of what we were, and then you would just throw this, then you would throw that value of x into here, and then this equation just becomes all in terms of y. And then if we have one equation with one variable, then I can put that into my calculator. I'd set it to 0, and this is, in your calculator, it'd be like setting this value as your function of y with respect to, and you would just treat even if this whole equation was in terms of y, in your calculator that would be the x variable. And so we'll probably end up doing that, and hopefully we'll do it twice just so we can have a double check, because that's where the math kind of gets a little bit tricky. Alright, catch on the flip side. Alright, hell yeah. So I printed off, oh man, it kind of cut this off, but we have the square root there, square root there, and square root there. Anyway, so I printed this off so we can use it a bunch of times just in case. This was the hardest part for me. I made a bunch of mistakes doing this. So now the question is, what do we want to solve for? I don't think it's going to be, I think this is going to be the easiest one, because hey, we got more terms going on here. So, and this has x, 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 and a y. So I'm going to solve this equation for y. And then once we get that, hopefully it's fairly simple, and then we can just throw it into here. But that's the weird thing, is like I'm still going to throw this into my calculator. Like when I get this equation in terms of y, I'm not going to magically just start to cancel terms, but that I should try though. You know what I mean? I think there's a lot of videos on at least like, how to divide polynomials, or I don't know, just how to simplify equations. But some equations can't be simplified, so I just find it ironic that I'm going through all these steps just to get this equation in terms of y, and then I just throw it into my calculator just to figure out how to optimize it. So I find that fascinating. Now the calculator uses methods that you could do by hand as well to like hone in on that answer. Whoops, sorry about that. But yeah, that was the only trippy thing that I was just like, oh yeah, it's not super satisfying to actually get something, but it shows you, I don't know, it shows you that you have a system of equations, and we're trying to find a solution. But I guess that is cool because we can get an exact solution. But I mean, like I said, we can get an exact solution just by finding the minimum point, honing in on that. Well, no, like I guess I said before, is like that would just, you still have to choose a value for y, and then you can optimize x. But then you have to go back and put that value in for x, and then try to optimize y. But yeah, you still could do that graphically. You could do this equation back and forth, optimizing x and y, which I also probably should do. Okay, so hell yeah. So we're going to take this, and we are now going to solve for y. I can see that this has a negative, so I could, I don't know how I did this. The first thing I did is like, well, let's just get that over there just cuz. You know what I mean? And we have a negative sign right there, so I can definitely do that. And then the other thing is like, can I cancel anything? Nope. Okay, so oh yeah, because I already canceled this when I brought down the half. That canceled that too. All right, so let's do it. So I have, and then I'm actually going to write this now with the square root. So I'm going to say this is 2x divided by the square root of 1 plus x squared. So that's this side. And then I'm going to take this to the other side. So that's going to equal, we're going to have 2 times 5 minus x And then this is going to be divided by the square root of 5 minus x squared plus y squared. Okay, hell yeah. So now we're getting somewhere. That's the first step, and I can see that I can factor out that 2. Alright, sweet. And what am I trying to find, though? I'm trying to find y, so let's get this upstairs. And so sometimes I like to do this. It's just like, okay, the next step I'm going to do is get this longer one upstairs, and then I'm going to get this over here. So then I'm going to have this, and then this. Okay, hell yeah. So I can visually see that. And then what am I going to do? Well, I have this up there. Now I'm going to square both sides, which is squaring that. If I know that this is a product, it'd be the same thing as like 2 times 2, and then I'm going to square it. That's the same thing as 2 squared times 2 squared. So it's also good to know how things are. Do they call that commutative or associative? Nah, that's like for multiplication. But I'm sure there's a term for this, like how one is similar to the other and they're identical. Just kind of the rules of exponents. Alright, so then when I do that, then I just have this stuff. So I have this squared plus y squared. Cool. And then I'm going to take this to the other side. So I'm going to have minus, you know what I mean, like this thing. Cool. And then this is going to be y squared. And then to get y, I just have to take the square root of it. Okay, so now I kind of know what I'm going to do. So I'm going to, and let's just do this in a few steps. So y squared is going to be this squared. So we have 5 minus x squared. This is the square root of this thing. No, that's not true. That's the square root of this thing. So we're going to have 1 plus x squared. And then, sweet. And then we're going to subtract, what are we going to, we're going to subtract this, 5 minus x squared. Sorry I did it in such tight steps, but I think that was I think it was useful to show this method. You know what I mean? Like why write things, especially when you're just trying to get the solution for yourself. And this is a way to not make so many errors, but I think there was a little disconnect. This was the longer one, so that got up there. This got up there, and then we squared them. So we're going to have 5 minus x squared. This squared is just 1 plus x squared. Okay, and then we had this over here. We squared both sides, so this just becomes this inside term, and it's up there. And now I'm going to subtract this 5 minus x squared. That's going to leave this y squared. Okay, we're up to speed. And we can see that we have a y squared on both sides. So I can even just, what do I want to do? Yeah, I'm going to factor that out. So we're going to say 5 minus x squared. This is going to be 1 plus x squared minus 1. Alright, hell yeah. And now this is y squared. Now I'm going to take the square root of both sides. Taking the square root of a product, same thing. 2 times 2 square root is the same thing as square root of 2 square root of 2. So square root of this is just 5 minus x. And then we're going to have the square root of 1 plus x squared. And this is 1 plus x squared minus 1. Oh, I didn't see that. So this just becomes x squared. Oh, hell yeah. So, yeah, did you see that? That's pretty sweet. So this is just x squared. Sorry to write it right next to it like it looks like a product. But this is just x squared. And then when we take the square root of this and take the square root of x squared, this just becomes x. Hell yeah. So now we have y is equal to 5 minus x times x. And, oh, yeah. I feel like I feel like I didn't do that right for whatever reason. Or that's not the answer that, well, maybe that is the answer that I got. I have no idea. Would this make sense? Let's type in something. So we're trying to find this value of y. which is hopefully something like 25. We know the value of x to be like 0.2. So 5 minus 0.2 times 0.2, and no, this is definitely, so we made some errors. So yeah, this is where I just do it again. And then hopefully I didn't make any errors. You know, if you're making errors, I don't know how far back you have to go. Okay, so we're gonna 1/2, bring down that, cancels with the 2, this to the negative half, 2x. This becomes bring down the half, everything on the inside to the negative 1/2, and then derivative of the inside, 2 times 5 minus x to the 1 times negative 1. Cool, and then this just becomes 0. Okay, hell yeah, so let's do it again. And then this becomes 2x square root. Oh, maybe this is where 1 plus x squared. Maybe I went wrong there. No. No, I followed that all the way through. Okay. All right, so that's that term. We're going to get this term to the other side, and I was chill with that. You know what I mean? So we're going to have 2 5 minus x. This negative, because we took it to the other side, that goes away. Both have 2's up top, so those go away. And then we're going to divide by the square root 5 minus x squared plus y squared. Alright, since I did this the other day, I thought I was going to get something like y is 5 minus x divided by x, and that would work. So 5 minus 0.2 divided by 0.2 is 24. But I'm just showing you that, like, man, I don't know how to not make mistakes. You know, you just do the best you can. But for whatever reason, we were supposed to divide by this x, and I don't see where that came into play. So let's do this. So I need to get this up there. So I'm going to just not oversimplify it. We tried, but we messed up. And then if I get that, oh, so there's that x. I didn't see that x. Okay, look at that. We have an x right there. I did not notice that. I did not, so that was the error. I did not see that. Just because I crossed out that 2, I did not notice that x. So now we don't have to do this full thing. It's also a good strategy just to go find your error, and then so if this x was up here, we would have to get this x down there. So we're going to have that x down there. We have to square both sides, so we're going to have this squared. And then we're going to take the square root of both sides. So then we can go through. Well, before we take the square root, that's what I did right here. We have 5 minus x squared, 1 plus x squared divided by 5 minus x squared. But this is all going to be over x squared. Yeah, so we just have everything divided by oh, but when we got to this point, we were still going to have this divided by x squared. Yep, so there we go. Sorry, it's so looks bad. But we were going to have, so this is going to give us, yeah, why when this gets, yeah, I don't know. Let's just run through it again. So I bring this up here. We're going to keep this 5 minus x. And then we're going to bring that to the top. So we have 1 plus x squared. Is that right? Yeah, 1 plus x squared. Cool. And now, and I'm going to take this x down there. So I'm going to divide by x. Alright, so now I can square everything. So I'm just going to square everything. I'm going to say this goes away, and then this goes away. Cool. Now I'm going to subtract 5 5 minus x. So let's rewrite this. So we have 5 minus x squared times 1 plus x squared divided by x squared minus 5 minus x squared. So yeah, squared. So now we can, and that's going to equal y squared. But we can factor out this 5 minus x squared. And then, yeah, so this term is the only term that has the x squared. This doesn't. So now what we're going to have is this. When we factor this out, we're going to have, and I might as well just factor this in right now. Because even right, well, let's see, what do I do to this? Oh, I was going to make a big math error. I was just like, well, if I put this under both of these two terms, I'm done. Or if I put this under that term, I'm done. I can take this and just multiply it by that. So that's, I got confused with, yeah, if I have this product here, it's only if I have a plus an addition or subtraction does this go under both terms. And as long as I have one thing in the denominator, I'm just good to go. Alright, so hell yeah. So I'm just going to do this as 1 divided by x squared plus 1. Cool. And then this is going to be minus 1. Alright, so there we go. So when I factor out this 5 minus x squared, and then I quickly put this under both of those, this is what happens. So this 1 minus 1, that cancels. And now I'm left with y squared is 5 minus x squared divided by x squared. So now we're good to go. We can take the square root of both sides, which is the same thing as taking the square root of the top and square root of the bottom. But I think you get it. So we have y is equal to 5 minus x divided by x. And that is our equation. And this jives. And like I don't know why you'd want to do a problem and just expect no mistakes and then get to something like this. And then how are you going to check your answer? I mean, you're just going to throw it in and then scratch your head and you're like, it's nowhere near anything that I would ever imagine. And I don't know. So it's just so good to have, yeah, because we know that if we go 5 minus 0.2 divided by 0.2, whoops, 5 minus 0.2 divided by 0.2, we get 24. So if x is 0.2, y is 24. And if x is 0.196, stored as x, 5 minus x divided by x, hell yeah, y is 24.5. We don't know that yet, but I already know the answer, so it's just kind of nice to relay that to you. Okay, so now what we do is we just take this equation and we plug in this value. And if we set it equal to 0, that's in our calculator. We're going to set, hey, like y is equal to 1. And then everywhere where we have, we are going to substitute this 5 minus x divided by x everywhere where we see a y. Oh, yeah, this will be pretty simple. And then everything will be in terms of x. And that'll be the variable in our calculator anyway. Alright, home stretch. And I'm going to write this out. So we have 5 minus x squared plus, hey, this squared. So we're going to have, I'm just going to write it like this, 5 minus x squared divided by x squared. So that's this squared, right? And then we're going to take it to the negative 1/2. Multiply this by 2, so we have 2, 5 minus x divided by x plus 1/2. Oh, I'm going to run out of room. 100 plus 2, 5 minus x divided by x, all that squared. Well, under that parentheses, whoops. We got a bigger parentheses, plus 10 squared to the negative 1/2, multiplied by 2, multiplied by 100 minus 2, 5 minus x divided by x, parentheses, negative 2. So yeah, how horrendous, but we'll be able to do it. And I don't know, I find this skill pretty decent, you know what I mean, where you're just, you know, trying not to make mistakes. 5 minus x squared divided by x squared. Parentheses to the negative 0.5. We got a 2 of 5 minus x divided by x plus 0.5, couple parentheses, 100 minus 2, 5 minus x divided by x, end parentheses squared plus 10 squared, more parentheses, negative 0.5. I just don't like how I can't see. That's the only thing about this calculator, and it's hard to scroll back and forth. Oh, and I didn't do my negative to the negative 0.5. There we go. Times 2. I guess times 2 times 100 minus 2 times 5 minus x divided by x, and parentheses times negative 2. Alright, if we did it right, this is going to give us the value of x. Yep, and we know that's going to be between, you know, I'm just going to do negative, I'm just going to do 0 to 0.5. And what's my range in y? Wait, what's this going to give? Oh, this is going to give me my, alright, so when x is 0, or what's this going to give us? Yeah, when x is 0, I don't know what it's going to give. So I'm just going to go zoom. Sometimes you don't know what the graph is going to give. And in this one, I have no idea. Alright, hell yeah. Whoops. So whoops, okay. So our value, I'm just going to trace it out. Hell yeah, so where it crosses is 0.2. And my y value, yeah. Oh yeah, so I was trying to find where this value was 0, which would be optimized. Yeah, so it's just kind of interesting solving two systems of equations. I solved this for y, put it in here, got everything in terms of x, and then where x is 0, I mean, that solves these two, basically it solves these two systems of equations. These systems of equations are partial derivatives. Where the partial derivative is 0 on both of these is where both of those numbers are optimized. And so back to our, you know, I guess in the end I'll draw a better picture. But this gives us that value of x. Whoops. So we got our 0. We're going to go left bound, right bound, find that 0. And our value of x is 0.1960784. Cool. So once we know that, then we can put that value of x into this equation. And then we can just treat this equation. Oh yeah, so that's fascinating. How, oh no, we can just, I'd lose my mind if I didn't see that. Okay, yeah, we definitely know we have this relationship between y and x. We just found x. It's 0.196. So let's throw it into here. So we have 5 minus x divided by x. And that gives us 24.5. So now we know our optimization. Our optimization is when y is 24.5 and x is 1.96. And let's kind of just draw this out so we can kind of see what's going on. We're going to have halfway about 24 right there. We're not going to go straight up. We're going to go over. And if this is 5, so let's do this to scale. 1, 2, 3, 4, 5. We're just going to go to 0.2. So we're hardly going to be at an angle there. And then we're going to go over to 24.5. Same thing here. We're not going to go straight down. 1, 2, 3, 4, 5. We're going to go to 0.2 at that angle, and then over to 24.5. So this distance right here, if this is 100, this is basically 25, so this would be 50 minus 1. So this distance right here is 49. And that's optimized. Hell yeah. And we use partial differential equations. And, you know, these problems, once you know the solution of, like, unfolding the box, I shouldn't have said that because well, no, everyone knows these. If you're looking this one up, you for sure know it. But I got the privilege of actually doing a couple of these this week, you know, totally forgetting about how to do the easy solution, enough said. And so I was able to work through differential equations to find the answers. And this one required two differential equations. We set this value as x and this value as y. This value is 5 minus x, and this value as 100 minus 2y. So that's what we did, and we optimized this length. So hell yeah. So I'm pretty satisfied with this one because it taught me how to use partial differential equations. And that was, yeah, that was pretty sweet. Alright, so that's all I got. And that's the partial differential equations. This was the main equation. And yeah, we kind of understand how we optimized. How you have to kind of set one constant and then change and then optimize the other one. So I kind of want to play around more with those to see if I could do an iterative method. But that'll be for another video. Alright, hell yeah. Thanks for joining me, and that's the video.